Hello everyone, Namaste. In this video, we learn to prove that Cobb-Douglas production function is the special case of CES production function. This video might be a bit lengthy, so now let's start. Let us write the general form of Cobb-Douglas production function. Q equals to A K alpha L 1 minus alpha. This is what we are intended to prove from CES production function. So now let us write the general form of CES production function. It is Q equals to A curly bracket alpha K minus rho plus 1 minus alpha L minus rho whole to the power 1 by rho. This is the CES production function. And from this production function we will prove our Cobb-Douglas production function. I will call it equation 1, and dividing equation 1 by A, let us divide it by A and divide it by A. This A get cancelled, so the remaining is QA equals to all minus rho plus 1 minus alpha minus rho curly bracket minus 1 by rho. Now I will take log on both sides. Log Q by A equals to log alpha K minus rho plus 1 minus alpha L, sorry, it's L minus rho power 1 minus 1 by rho. And using the property of log, we know that log x to the power A, we can write it A log x. This is the general property of log, and I will follow this property. Q by A and minus 1 by rho ln alpha K minus rho plus 1 minus alpha L minus rho bracket. Now I will simply suppose that this numerator part is equal to ln m, and I will assume this part as ln n. So now I can write Q by A equals to minus ln m divided by ln n. Now I will take limit on the both sides. Limit rho tends to 0 ln Q by A equals to minus limit rho times 0 ln m by ln m. Oh, sorry, and n. So now I will take the limit individually for m and n. So limit rho tends to 0 ln m equals to limit rho tends to 0, and what will be our ln m? It's nothing but ln alpha. I will write it here, alpha k minus rho plus 1 minus alpha L minus rho. And when I substitute its value, then this term will be alpha, this term will be, sorry, it is alpha. Let's use eraser for it. This is 1 minus alpha, and here alpha will be remaining because it will be 1, this will be 1. So now ln alpha plus 1 minus alpha, these two terms get cancelled, and ln 1 equals to 0. Similarly, limit rho tends to 0, ln n equals to, it's simply 0, because ln n it is itself rho, so it will be 0. So now from here, the value of limit we have derived is 0 by 0, because the value of ln m is 0, limit, after taking limit, and the value of limit ln n is also 0. So now we will use L'Hospital's rule. L'Hospital's rule. Sorry, my handwriting is a bit rough. We will use L'Hospital's rule. L'Hospital's rule says that if the limit is indeterminate, then we shall take the limit on its differentiation. So now we will find the differentiation of ln dash m. We will find ln dash m and ln dash n, means that we will find the first difference of ln m and ln n. So finding the first difference, if I differentiate this term in the circle with respect to rho, then I will get the value of ln dash m. It means that we are intended to differentiate the value in this circle with respect to rho. So now let's start. I will simply write is as differentiate ln m with respect to rho equals to, its value is alpha k minus rho plus 1 minus alpha L minus rho, and we will differentiate with respect to rho, and we have limit 2, we have here ln, it's ln. So since there is ln, we will use the log operation for our differentiation, means that we will write ln alpha k minus rho plus 1 minus alpha L minus rho. Differentiating, we will match this numerator, and we will simply write here alpha k minus rho plus 1 minus alpha L minus rho, and we'll cross multiply it, alpha k minus rho plus 1 minus alpha L minus rho, and differentiate equals to rho equals to, and I will use the rule of differentiation in case of log. Let's recall it. D ln x divided dx equals to 1 by x. I will use this rule, and using this rule we will get the value as alpha minus rho plus 1 minus alpha L minus rho times. I will now differentiate this term with respect to rho. It will be alpha L and k minus rho. It's k plus 1 minus alpha. It will be uh, L and L to the power minus rho. Its bracket close. I have directly done the differentiation, and I want to show its process. It is that differentiation with respect to rho alpha k minus rho. I will simply do this for this portion, and the process is same for the second portion. It will come outside d rho k minus rho. So now here we must recall our one formula, that is y equals to e to the power x, and if we need to differentiate, then we need to take the log form, that is ln y equals to x ln a. I have directly used the logs property, and y equals to e to the power x ln a. And now if I differentiate this with respect to x, then it will be dy by dx equals to d by dx e to the power x ln a, and it will simply be x ln a e to the power x ln a. This means that, sorry, here it's no x, it's, we must only write ln a because it is constant, and it will be ex ln a. So ex ln a ln a, it's simply ex equals to y, it equals to y, and y equals to e to the power x, so it's e to the power x. So I can also write here ln, here a means k, it's k, and minus rho means x, so I will write k minus rho. I think you have understood. This is simply uh, the property the um, of the different of the variable in the power form, and this is its derivation. So in this way we can write this value. So now we shall move on. It will be easy if we take limit here. Limit, I will write n dash m rho tends to 0. Then if I replace the value of rho in this portion, then in this result, then the value will be ln k to the minus 0 plus 1 minus alpha ln l minus 0 or divide by alpha k 0 plus minus alpha l minus 0. It will simply equals to alpha ln k plus 1 minus alpha ln l over, it will be equals to 1. So it's equals to ln k alpha plus ln l 1 minus alpha. I can further write as ln k alpha l 1 minus alpha. This is the final result. And in this step I have used the property of log, means that alpha ln k, I can write this alpha as a power of k. So now for ln n, we will simply take the derivative of rho. It's equals to that its rho, its value is rho, so it's equals to 1. So now following the L'Hospital's rule, let's write in our next portion. L'Hospital's rule limit rho tends to 0 q by a equals to limit rho tends to 0 ln m by ln n equals to limit rho tends to 0 ln dash m divided by ln dash n. So now since we have already done the limit operation, we can write qa equals to, let us simply replace the value of limit rho tends to 0 ln dash m. It's, I think here we have log, it's log, it's equals to ln k alpha l 1 minus alpha, and it's simply 1. So we can write q by a equals to k alpha l 1 minus alpha L1 minus alpha Q equals to A K alpha L1 minus alpha. This is what we were intended to prove. So it's proved. So we were initially intended to prove this, and we have finally proved the Cobb-Douglas production function is the special case of CES production function. Thank you.